Welcome back to ECE 501B. You have two more homework assignments. The first one is due on Wednesday. That's homework number 7. Homework number 8 is due the following Wednesday. And your project is due that same day on the 7th. There's a lot of things due on the 7th. The teacher course evaluations are due by the 7th. And I would appreciate you helping me learn how to improve the class and what was done right and what could be improved on the TCEs. The final exam is not on a Monday or a Wednesday, it's on a Tuesday, and it's a little bit later than normal, so it's going to start 2 hours later than the class would normally start, and it's on Tuesday the 13th of December. Today, or actually the remaining part of the semester, we're going to move through at a quicker pace the chapters. We'll cover chapter 8 and 9 today. Actually, chapter 9 we will cover virtually, I'm expecting, meaning we'll just say similar ideas can be applied to the real vector space. That's chapter 9. Chapter 8 is what we will work through today or look at. And one of the topics is that of generalized eigenvectors. And what we will find is that there are possible operators that do not have distinct eigenvalues, or they maybe for one particular eigenvalue do not have a full complement of eigenvectors. There may only be one eigenvector, and maybe you have multiple eigenvalues and only one eigenvector for that repeated eigenvalue, and we need to come up with a way to maybe not completely diagonalize a matrix, which was the nice representation that we've been looking at, but get close to a nice matrix representation, and that means we may go into a Jordan form, and we'll talk about a Jordan form representation. And these generalized eigenvectors are needed when, in the complex vector space case, we do not have a normal operator. And in the real case, if we do not have a self-adjoint. And you can see that you can create all sorts of operators that will not be normal and they will not be self-adjoint in either the complex or real. And those operators, then, we need to talk about generalized eigenvectors, really to create a bigger pool of vectors with which to transform these operators to get our matrix in that basis as close to diagonal as possible. It won't be purely diagonal. Then we'll talk about the characteristic polynomial and the Cayley-Hamilton theorem. And then after chapters 8 and 9, we'll get into, finally, the determinant, which in a lot of linear algebra books you might see a determinant introduced much sooner, but here we're looking at linear algebra done right, and so we delay the definition and the use of the determinant until the last chapter in the book. And we'll also look at the trace of a matrix. In chapters 8 and 9, we're talking about this idea of generalized eigenvectors, and what I want to do is first start with sort of the concept behind that, and then we'll try to create ways to find these, or even go through some examples where we are finding these generalized eigenvectors. The basic idea is as follows. The spectral theorems, which are the ones for complex vector spaces and real vector spaces, tell us something about what we can do when we have self-adjoint operators. So the spectral theorems tell us that self-adjoint operators have eigenvectors that actually form an orthonormal basis. And what does it take to be a basis? It has to span the space, and they have to be linearly independent, those vectors. And so if our space is n Nevada big, then we have to have n vectors, and they have to be linearly independent. And in this case, if we have a self-adjoint operator, they can be more than that. We can actually normalize those if we now have an inner product space. So we can now have these vectors that are normalized to have a norm of 1, and they can form a basis with which we can then diagonalize matrices. We really overspecified the basic idea when we said self-adjoint. In a complex space, we don't need it to be as strong as self-adjoint. The self-adjoint can be relaxed. And it can be relaxed to just being a normal operator. Or normal operators. And what that basic idea is saying is that equivalently, or equivalent to saying that the vector space V has a direct sum decomposition in terms of one-dimensional, or now just think of single columns as column vectors essentially, in terms of one-dimensional invariant subspaces. Or V is now U sub 1, where U sub 1 could be the vector in the null space of T minus lambda sub 1I, U sub 2 similarly, and we're now decomposing that vector space into these subspaces U sub 1 through U sub n. Or written a different way, we could say that U sub 1 now is this null space of T minus lambda 1I plus the null space of T minus lambda sub 2I. That's representing U sub 2, etc., down to the null space of T minus lambda sub n I, where all of these lambdas, lambda 1, lambda sub 2, up to lambda sub n, are distinct. And today what we want to talk about is what happens when we don't have these self-adjoint operators. Or in the case of complex vector spaces, non-normal operators. By that, I'm meaning we may not have a complete set of eigenvectors. We may not have n eigenvectors. We may have an insufficient number of eigenvectors. which, said another way, we can't decompose our vector space in a one-dimensional way, can't decompose in a 1D way. And if that's the case, then a pure diagonal matrix may in fact not exist for that particular operator. What we want to do, though, is realize that, in fact, we can decompose in a way similar to what we have been, but now we simply start raising this t minus lambda sub I to higher and higher powers. And what's in the null space of that higher power of t minus lambda sub I will be these generalized eigenvectors associated with that particular eigenvalue. But can decompose as V is equal to the null space of t minus lambda 1 I to the n, direct sum with the null space of t minus lambda sub 2I raised to the n, direct summed with the null space of t minus lambda sub m I to the n, and now I am making a distinction between m and n. M is Michigan and n is Nevada. I'm raising this to the nth power, and I only have little m distinct eigenvalues, where m is now less than or equal to n. N is the dimension of our underlying vector space, and when we need it, d sub I is going to be the dimension associated with the null space of t minus lambda sub I to the n. And d sub I we'll refer to as the multiplicity of that particular eigenvalue, lambda sub I. D sub I is the dimension of the null space of t minus lambda sub I to the nth power. And that is the notation that we will use to indicate the multiplicity of lambda sub I. Let's now look at what we can do, or what that really means in terms of finding vectors in these null spaces. And that's what's leading us then to this new concept of generalized eigenvectors. Before, we've really just been talking about eigenvectors. Now we're opening that up so that we can talk about more general operators than self-adjoint operators or normal operators. We are allowing for more options in terms of what kinds of operators we're working with or can work with. Suppose now we are given a linear operator, t, on our vector space V, and lambda, an eigenvalue, of that linear operator. And that means then that TV is equal to lambda V for the eigenvalue eigenvector. But now we want to generalize that and say a vector V in our vector space capital V is what we will call a generalized eigenvector of our linear operator T, if, when we look at t minus lambda times the identity matrix raised to the jth power v, that v lives in the null space of that operator for some non-zero j. So you could say j is greater than 0 or j is greater than or equal to 1. And we've already seen this, which is what I'm indicating in this note. If we can find a vector v when little j is equal to 1, that vector v is an eigenvector. When we have to go up in powers and make j 2 or bigger, then we have these vectors, and we'll call them generalized eigenvectors. But if j is equal to 1, that's what we've already been defining as an eigenvector. Let's look at an example, and this is not the same, but it's like, very much like, an example in the book, and the example in the book is example 12 in chapter 8 of the 3rd edition. But it's not quite that same example. It's close, but we can get the same idea. Suppose that our operator is in 3 space, meaning we have 3 coordinates in our domain vector, and suppose that the linear map T takes the vector z1, z2, z3 into the 3 vector z sub 2, comma 0, comma z sub 3. That's our linear operator. What's our eigenvalue, eigenvector relationship? Typically, how do we write that? If I use z, it's going to be tz lambda z, which now says that if I look at the output, which is tz, that's on the left side, and that I said was z sub 2, comma 0, comma z sub 3, that's supposed to equal some scaled version of the original vector z. Or that's now equal to lambda z1, lambda z sub 2, lambda z sub 3. And if you're not real keen on what we're talking about today, one thing you could do is you could think of this as a review for the final exam. Now let's just kind of step through this way. How do we find these lambdas? How do we find the z's? How do we find the eigenvalues and the eigenvectors for this linear operator? In a sense, we're reviewing for the final, right? What does this tell us? Now if we simply equate coordinates, we will try to find relationships relating the elements in z, or the coordinates in z, and the values of lambda, or our eigenvalues that satisfy this equation. If we look at the first coordinate, we see that z sub 2 is equal to lambda z sub 1, and we want that to be true for all values of z1, z2, and lambda. Or for what value, I should say, for what values of lambda will this be true for all values of z1 and z2? If I make z1 equal to 1 and z2 equal to 7, what value of lambda (7) is bugging you? But the only way that this could possibly be true is to make lambda equal to 0, right? So now if we force lambda equals 0, and this may force particular values for z1 and z2, but if we say lambda is equal to 0, this is then, if true, for all z1 and z sub 2. it really doesn't make much sense if, because lambda can't be 7 since, or maybe I should quit with 7. Lambda can't be 8, lambda can't be 10 for any value of z1 and z2. So let's just force it to be 0. The second coordinate now says that we have 0 is equal to lambda z sub 2. And what does that say? For all values of z sub 2, and now this makes our first coordinate more consistent. If we now force lambda to equal 0, that's true for all z sub 2. And now we can say that that's sort of forcing our hand on the first set of relationships, but now the last coordinate says that we have z sub 3 as lambda z sub 3. And here, now we can see that, oh, in fact, lambda is equal to 1 will work in this case. We have z sub 3 equal to itself. Or we've now identified our 3 different eigenvalues for that 3-dimensional operator, 0, 0, and 1. So let's look at the eigenvectors. For that, or first maybe let's just look at the matrix representation of that operator T. And maybe I really needed to slide up one more. This will now tell us what needs to be applied to z1, z2, z3 as a vector to produce z2, 0, z sub 3 as an output. Or what is going to happen in the top row of A in order to produce z sub 2 in the first coordinate of the output vector. It needs to pull off the second coordinate of the vector in the domain, z1, z2, z3. To produce a 0 in the output, we don't want to scale any of the coordinates in our input vector, z1, z2, z3. And to find as our output result z sub 3, we need to pull off the last coordinate. If you've had an earlier class in linear algebra, you might actually recognize this as a particular form of a representation, and it's actually the Jordan form of a matrix A, meaning it's block diagonal with each block containing on its diagonal the eigenvalues of that matrix. We have 2 eigenvalues in the top 2 by 2 block, and in the off diagonal we might have 1s. So this is now a Jordan form representation. Not that we've derived that or said anything, it just so happens that that's the way that that particular linear operator was set up for the standard basis. Let's now look for the eigenvectors. This is now our matrix representation of A. It just happens to be a Jordan form representation. Let's look at what happens when we try to find eigenvectors associated with lambda equal to 0. For lambda equal to 0, we're interested in the matrix A minus lambda I when lambda is equal to 0, or vectors in the null space of that. Here, that's just the A matrix. If we scale the identity by 0, we're now interested in what vectors lie in the null space of that matrix. we want to find values for z1, z sub 2, z sub 3, the three coordinates of our vector that satisfy that equation, that map to the 0 vector. If we look at the first row, what does that tell us? That says z2 is equal to 0. The second row doesn't give us any information. It says 0 is equal to 0. Let's look at the third row. And the third row now says z3 is equal to 0. What does that put constraint-wise on the first coordinate? Does it put any constraints on the first coordinate? No. So z1 can be anything, and it will be in the null space of that matrix. So we typically just normalize that vector as 1, 0, 0 to be the eigenvector associated with that eigenvalue, or z1 now is anything. And our eigenvector now is 1, 0, 0. And how many different ways could we, or how many different vectors could we create from that equation of a minus 0I? Could we find any more vectors than a scalar multiple of this that will satisfy this equation or set of equations? No, this is the one and only eigenvector associated with that eigenvalue 0, which is actually repeated. We have two eigenvalues at 0. But this v is then an eigenvector for lambda equal to 0. It would have been nice if we would have found another vector that was in the null space, or if we had a two-dimensional null space for that a minus 0 times the identity matrix. What about lambda equal to 1? Now we are looking at a minus lambda I with lambda equal to 1. We're subtracting 1 on the diagonals. And we started with a 1 here, and we started with a 1 there. So let me just get rid of that 3, 3 entry and realize that that's now 0. And what we want to do now is find vectors that lie in the null space of that matrix. Or we now have minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0 times our 3 vector. And we need this, which generates 3 equations to be simultaneously true, those 3 equations. The first row tells us that we have minus z1 plus z sub 2 equal to 0, or that says that z1 is equal to z sub 2. The second row says we have minus z sub 2 equal to 0, or z sub 2 is equal to 0, and now if we combine these, that now says that since z1 is equal to z sub 2, both of those coordinates have to be 0 in this vector. And what does that say about constraints on z sub 3? If you look at that matrix, the third column is all zeros. That's what's weighting z sub 3. Z sub 3 can be anything, and it will be in the null space or give rise to a 0 out. So z sub 3 is anything. And now our eigenvector, let's say a normalized eigenvector for that eigenvalue is 0, 0, 1. How many eigenvectors did we end up with? 2. How many really did we need to form a basis? We would have needed 3. We don't have 3. We only have 2. So now we need to find another vector somehow, and that somehow is by looking at powers of a minus lambda I for for the different eigenvalues lambda. Or we're now looking at the question, what about the other eigenvalue at lambda equal to 0? It's feeling a little bit lonely. It didn't have an eigenvector that popped up with it. In this case, lambda equals 0 is repeated. And unfortunately, for that particular case, this particular operator didn't have 2 linearly independent eigenvectors associated with that repeated eigenvalue of lambda equal to 0. Or there was only one eigenvector associated with lambda equals 0. Or another way of saying that, if we looked at the dimension of the null space of a minus 0 times I, and I'm being very explicit with the power of that a minus 0 times I, that's raised to the first power, that was just one-dimensional, the null space. Because in that particular case, what did we find? We found that Z2 and Z3 had to be 0, and we only had a 3 vector. The only free variable was the first coordinate, and that only gave us the one vector associated with the eigenvalue lambda equals 0. So we have a one-dimensional subspace for this particular eigenvalue. And this is then what's calling for or needing us to create something more general. So we now need a generalized eigenvector to create a basis for our underlying vector space, which in this case was three-dimensional. And to see what we can come up with, let's go ahead and examine a higher power on the argument of the null space. Suppose we now look at a minus 0, that's our lambda, times I squared. So let's raise a minus lambda I to a higher power. For this particular example, for lambda equal to 0, this is really just a squared. And A, the matrix representation of our operator, first row was 0, 1, 0. The second row was all 0. The third row only had 1 in the third column of the third row. And we want to now multiply that by itself. And now, have you selected a personal favorite on how to multiply this? Instead of going row, column for 9 different entries, do you like to look at it from the row perspective or from the column perspective, or does it matter? You like to hit it with the columns. So if you think of it from the column perspective, you're now looking at the rightmost matrix and saying, okay, the first column in my product is going to the first column is going to be 0 weighting all 3 columns in the first matrix. So I now have 0 times the first column plus 0 times the second column plus 0 times the third column, or I now have all zeros. The second column is going to pick off and weight only the first column in the first matrix. And that's all zeros, so that's now 0, 0, 0. And the third column is going to pull off and weight the third column in the first matrix by a scaling factor of 1, or we now have that for our product. And you could have seen that also by looking at the row perspective. If you now look at the first matrix and say, oh, the first row in the product is going to be a 1 times the second row in the second matrix, and the second matrix is all zeros. So now the top row has to be all 0. The second row is weighting all rows by 0, so that gives me an all 0 second row. And the third row is just going to give me 1 times the third row, which is 0, 0, 1. So you can get that same result by looking at this 2 different ways. But what we were after is we're really wanting to know what's the null space of A squared. What 3 vector will allow you to end up with mapping into the 0 vector? What can I put in each of these coordinates? What can z sub 1 be? So now you're saying, oh, z1 being multiplied by 0, 0, 0, 0, 0, 0, 0, 0, 1, read off by rows. What can z1 be and still give us 0? It can be anything, right? Z sub 2 can be anything, but z sub 3, we can't have that being equal to anything because it's going to be picked up by that third row as the 1. And so this is true now for z1 and z sub 2 in our field. Where another way of stating this is actually the subspace containing the generalized eigenvectors for lambda equal to 0. Or we could also write that as a direct sum decomposition. We could say one vector could just be the first coordinate direct summed with a non-zero second coordinate, and that too will be a way to do a direct sum decomposition of this subspace that has arbitrary first 2 elements in the 3 vector. And that now says that for this particular operator, we can now decompose it, or we can find a way of spanning that as the subspace associated with lambda equals 0, which we have now learned can be represented by z1 and z2 being arbitrary, direct summed with the eigenvector associated with lambda equal to 1, where z sub 3 is arbitrary. So that this is now the subspace containing the generalized eigenvectors for lambda equal to 0, and this second subspace is the subspace containing the generalized eigenvector. That's just one-dimensional for the eigenvalue lambda equal to 1. One thing that we can observe is that we could have gone to higher and higher powers of that a minus lambda I and still found this same set of subspaces falling out. By that, I'm suggesting the following relationship. If we look at t minus lambda I to the j v, and we know that that's equal to 0 for some lambda and some v for a fixed j, then we can also say that t minus lambda I to the j plus 1 times v is equal to 0. And that's true because if you look at t minus lambda sub I to the j plus 1 times v, you can now see that as t minus lambda I times t minus lambda I to the jv, but this was given to be 0, and the 0 vector mapped through anything, any linear map, is going to give us 0. Which really says that all generalized eigenvectors are solutions of t minus lambda sub I to the n, or vectors in the null space, where those vectors are v, of t minus lambda psi I to the n, where n is the dimension of our underlying vector space, capital V. We're now able to start to find these generalized eigenvectors. Before, we were stuck with the eigenvectors and we had to create more to find a basis. What can we say about general operators on a complex vector space? Remember, we can put any operator, call that T, over this field of complex numbers into what kind of form? Given any linear operator, do you remember how we can translate that or find a basis for to maybe make the representation cleaner? It can be upper triangular, can it? So any linear operator can be transformed into an upper triangular form. And I'll just say that that's UT form. What do we know about the scalars on the diagonal? Those are the eigenvalues. What we don't know, though, or what we may not have, is a unique upper triangular representation. What's above the diagonal may not be unique for that particular operator. Usually not a unique upper triangular form. And when is that upper triangular matrix or representation actually purely diagonal. That upper triangular is only diagonal when you have a complete set of regular, not generalized, regular eigenvectors. So it's only diagonal if we have enough regular eigenvectors. But in general, these eigenvalues can be repeated. And when they're repeated, sometimes they can have regular eigenvectors, a multiple set, and sometimes they can't. In the last example, we couldn't find more than one eigenvector for that repeated eigenvalue of lambda equal to 0. And just to repeat what we've already defined, let's just say that each lambda is repeated, to establish notation again. Each lambda is repeated a number of times equal to its multiplicity. And we were calling that d sub I, where d sub I is equal to the dimension of the null space of t minus lambda sub I to the n for I equal 1 to up to possibly m distinct eigenvalues lambda. Let's look at another example. Suppose that somebody says that the matrix representation of a linear operator t ends up being 5, 1, 0, 5. So this matrix representation of t is already upper triangular. And in fact, it's a Jordan form. It has our eigenvalues on the diagonal, and the off diagonal, one above the diagonal, is a 1. So this is a Jordan form. And if somebody said, oh, can you tell me what the linear operator is if we applied that linear operator t to a 2-vector z1, z2, what would the first coordinate be? If this is the matrix representation of that linear operator t, what's the first coordinate if we now apply this linear operator to z1, z2? And what's the second coordinate? That's just 5, z sub 2. Again, reviewing for the final. So this is now a matrix representation. The eigenvalues are on the diagonal since it's upper triangular. And its multiplicity, or how many times is that eigenvalue repeated, is 2. Suppose now we look to see, can we find regular eigenvectors for that particular eigenvalue 5. So now we're looking at, well, maybe I shouldn't get so sloppy. Matrix representation of t minus 5i becomes what? If I subtract 5 from the diagonal, I get zeros on the diagonal, the 1 stays put, and I haven't touched the off diagonal. So that's the matrix representation of t minus 5i. are there vectors that, when multiplied by that matrix, or are there vectors in the null space of that matrix? And if so, what are they? If I now hit this or on the right with a 2 vector, z1, z2, what can I have in z1, z2, coordinate-wise? Can I have anything in the z2 coordinate and have the result mapped to the 0 vector? No. I have to force the 0 coordinate to a 0. Or in fact, a normalized eigenvector, the only one for that particular eigenvalue of 5 is 1, 0. Or the dimension of the null space of, if I call the matrix representation of TA, A minus 5I is just this vector 1, 0. Meaning, we need to go to a higher power of that matrix minus 5I. In this case, let's say we have the matrix of T minus 5I squared. If I now multiply or square that matrix, what do I end up getting? If I put a copy of that on the right, what happens in the bottom row of the product? If I have 0, 0 weighting both rows of what's on the right, is it clear that I have all zeros in the second row? What do I get if I now look at the top row? I take 0 and multiply it by the first row, and I get 1 times the second row, but the second row is all zeros. So I hope that it's clear that the result of squaring that matrix 0, 1, 0, 0 is the identity, or I'm sorry, the 0 matrix. What vectors can you find that, when multiplied by that, will give you the 0 vector? Any vector in R2 or in the two-dimensional space. So let's now just make those consistent with our earlier choice. Let's say we now have E1 is 1, 0 again. And if that's the case, then we could find a linearly independent vector to that to be 0, 1. Or now we can say that the dimension of the null space of the matrix representation of T minus 5I, well, maybe I'll do it even more generally, since lambda I, that squared with lambda equal to 5 is equal to 2. And that two-dimensional space, I hope it's clear, is spanned by the E1 and the E2 that I've identified. In this case, E sub 1 is indeed an eigenvector, and E sub 2 is this new generalized eigenvector that we introduced. And if we want to, well, we can show that the dimension of these or the sum of these multiplicities from I equal 1 to m, we only have m of these multiplicities, or m distinct eigenvalues. That's equal to the dimension of our underlying vector space, capital V. Now that we have this definition of multiplicity, or this concept of multiplicity, we know the eigenvalues, we have m of those. Now we can actually create a polynomial from this set of eigenvalues and their multiplicities. And the one that we're interested in to start with is what we will call the characteristic polynomial, associated with a given operator. But here, the characteristic polynomial in general, if we call that q of z, is now going to be z minus lambda sub 1 raised to its d1, where d1 is the multiplicity of lambda 1, z minus lambda sub 2 raised to the d sub 2 power, and on to z minus lambda sub m raised to the d sub m. And I hope it's clear that the roots of this characteristic polynomial are in fact the eigenvalues. Meaning the eigenvalues, any eigenvalue will force that polynomial to vanish or to equal 0. If we plug in z equal to lambda sub 1, it vanishes. If we plug in z equal lambda sub 2, it vanishes. So lambdas are eigenvalues, are roots of that characteristic polynomial. So obviously roots of q of z are the eigenvalues. Now that we have that, we can actually use that to establish relationships on powers of our operator, or matrix representation of our operator, and that's coming to us by the Cayley-Hamilton theorem. For the Cayley-Hamilton theorem, we can say, suppose we're given now a vector space that's a complex vector space, V, a linear operator T on that complex vector space, and a polynomial Q of Z, which is the characteristic polynomial of that linear operator T. The Cayley-Hamilton theorem then says that if we replaced Z with our linear operator T, then that's going to be 0. And the characteristic polynomial of T is not hard to generate. We just have to find the eigenvalues of that linear operator and then create this characteristic polynomial. So we need to find the multiplicities of our eigenvalues and then use that to create our characteristic polynomial. And we won't go through the proof, but let's look at some examples. And so that we don't spend time trying to find eigenvalues again, suppose that we have our linear operator is on a 3 space, and the linear operator maps as output z1, z2, z3 into the 3 vector z2, 0, z sub 3. we've already established that the matrix representation of T, which we'll go ahead and recall A, is 0, 1, 0, 0, 0, 0, 0, 0, 1, reading it off by rows. And since that's upper triangular, we can identify the eigenvalues as those scalars that are on the diagonal. And in this case, those are just 0, 0, and 1. And with that set of eigenvalues, with the multiplicities shown explicitly, we have two distinct eigenvalues, 0 and 1, with 0 being repeated, or its multiplicity is 2. The multiplicity of the eigenvalue at 1 is 1. We can now create the characteristic polynomial of that linear operator T. Or Q of z is now z minus lambda 1 times z minus lambda 2. Let's call lambda 1 and lambda 2. We're abusing maybe our notation a little bit. And then z minus lambda sub 3. Or now we have our characteristic polynomial is actually z squared times z minus 1. Cayley-Hamilton says that Q of t, where now we use t, the operator, to replace our z's, says that if we square the operator and multiply it by t minus 1 times the identity matrix, that's going to give us the 0 matrix, or the 0 map. Or if we look at this in terms of the A matrix, the matrix representation of T, that's now saying that A squared times A minus I is equal to 0, where A is now the matrix representation of that linear map. And I'm assuming that you want to check that. So A squared, we've already created, but let's just write it down again. That was the top two rows were all 0, and the last row just had a 1 in the third column. If we look at A minus I, we end up with minus 1, 1, 0 in the top row, 0, minus 1, 0 in the middle row, and nothing in the bottom row. And if we're interested in this matrix polynomial Q of A, which is now A squared times A minus I, we're saying we want to know what's the result of applying A squared to the matrix A minus I. And in this case, it might be easier to think in terms of rows, since the leftmost matrix is mostly all zeros. Or since the top two rows of the left-hand matrix are all zeros, we know that the product has to produce zeros in the top two rows, and now all we have to do is pull off the third row in the second matrix and scale it by 1, but the third row is already 0. And so, in fact, we did check that the matrix representation of that linear operator does satisfy the characteristic polynomial, or that's the Cayley-Hamilton theorem. Another result that we can look at concerns the null space of a polynomial of t and the range of that polynomial of t. The null space and range of P of t are invariant under t. Meaning if we apply any vector from the null space of P of t or the range of P of t, or if we map that through t, we'll end up back in that null space or the range space. Where this now says if we have a linear operator t on a vector space V, and we have a polynomial p that's in our set of polynomials, p of f, then the null space of P of t and the range space of P of t are invariant under t. Let's look at the null space piece first. So let's let V belong to the null space of this polynomial of t. Or that says that if we had this polynomial in t, the vector V, when operated on by that polynomial, maps to the zero vector 0. We can also look at the following relationship. Suppose we now have this polynomial of t operating on TV. But in fact, we can claim that this P of t and t, the linear operator, actually commute. And we'll explain that in just a minute, but let's use that fact. If P of t and t commute, what can we do with what's on the left-hand side? We can interchange t and P of t, so that now we have t operating on P of t, V, but what did we assume P of t, V was? That was 0, and any operator, linear operator, that operates on the 0 vector puts us back in the 0 vector, and so now we know that any vector that starts in the null space of P of t and is mapped through the linear operator t stays in the null space of P of t. Or we could say, why do P of t and t commute? What is P of t? That's a polynomial in powers of t, and the coefficients, or the scalars, are just that. They're scalars. So these are linear combinations of powers of t. P of t is just linear combinations of powers of t. And what happens if you hit that on the right or the left with t. You haven't changed anything, have you? So if you had t cubed times t, that's the same as t times t cubed. It's t to the 4th. And the scalars just slide through. And so that proves this fact, or that sort of explains this fact. And this particular piece now shows that T of V is in the null space of P of T if V starts in the null space of P of T. And I think I will say that the range of T it's similar. You just have to start piecing that together, and I'll refer you to the text for that. But it's the same. You're really using this fact that P of T and T commute, and you can use that to help you explain that the range of P of T, this polynomial of T, is invariant under T. So what? Well, now we can actually look at nice decompositions in general. So it gives us a nice, all of this generalized eigenvectors, etc., allows us to come up with a nice decomposition. And a nice decomposition really says what? We're loaded up with zeros in our matrix representation. Or if we look at sort of a combination of several theorems, let's say it's theorems 821 and 829, and this is a description of operators on complex vector spaces, we can now make the following statement. Suppose that we have a complex vector space V, or for V, a complex vector space, and T a linear operator on V, and lambda 1, lambda 2 up to lambda sub m, the distinct eigenvalues, of T, with invariant subspaces G1, G2 up to G sub m, the corresponding invariant subspaces, and those subspaces G1 through G sub m are possibly not one-dimensional, if we have generalized eigenvectors. And I'm using this notation that G of lambda t, I didn't show all the arguments of G, is equal to the null space of t minus lambda sub I to the dimension of V. So if we have that notation, we can make three claims. One is there is a direct sum decomposition of V of the form V is now equal to G1 direct summed with G sub 2 direct summed with G sub m. D, these G's, G sub j is invariant under our map T, where G sub j is equal to what I said before, the null space of T minus lambda sub j I to the n. N is the dimension of V, and C, there exists a basis of our underlying vector space with respect to which our linear operator T is maybe not diagonal, but is block diagonal, meaning the matrix representation of T is now some A1, A2, A sub m, and everything else off of those blocks are 0, and further, each block in these A's, each block is upper triangular. And that is what we will take from Chapter 8, and Chapter 9 is this repeated for real vector spaces. But here, you've been patient enough, you've allowed me to go a little bit beyond the time, I appreciate that, but the main thing is, now that we have these generalized eigenvectors, we can block diagonalize any of these linear maps, or these linear operators. And that's what I want you to take away from this, where these blocks are as big as the multiplicity of that particular eigenvalue. And we'll pick up with Chapter 10 on Wednesday.